It's probably fair to say very few of our customers that are cooling things down aren't heating something else up first. If you think about it, why would people do cooling? They're not doing it just for the fun of it. So somebody else is doing the heating. So we'll see a term that I've coined. I wish we could use it for our footballing team because something similar has been coined by the Dutch. But total energy is the way I think of it. So total football would be nice, but we'll just keep lumping the long ball up the park for now and see how we go on. So first of all, the pressures that our customers are facing are wide and varied. If you think rising energy cost is enough to make you think differently, then the government come along and lay on another layer of trouble on top of it. And the one that's the first part of the presentation is the carbon reduction commitment. If you've not heard of the carbon reduction commitment, you're extremely lucky because that probably means that your company was either exempt or didn't have to register for it. But it's not actually something that applies to every business. It's only businesses over a certain size. But to put it in context, and I'm not sure of the accuracy of this, but somebody told me not so long ago that a large supermarket, the impact of the carbon reduction commitment plus rising energy costs within 5 years will wipe out their profit. Now that's quite a sobering thought, really, that these supermarkets that we hear making huge amounts of profit, rising energy costs and carbon reduction commitment, which is basically another tax to encourage people to be more energy efficient, will wipe out their profits. So what are we going to do about it? Well, first of all, these slides, a bit about the carbon reduction commitment. We'll talk a little bit about low-hanging fruit, an expression that everybody is familiar with. Sometimes we even find that the fruit is fully ripened and lying in the ground, but nobody's picking it up. Techniques for rapid engagement. A couple of examples that we've seen show that really you can step into it quite slowly, or you can try and come up with a slightly more aggressive plan. And then this vision for total heat or total energy. And there's a case study about that towards the end. So carbon reduction commitment is mandatory for certain businesses. It's entirely derived about energy efficiency, range of drivers, and it's basically large businesses in the UK that have a 6,000 megawatt hours per year energy consumption, which roughly equates, if you run your plant for 4,000 hours a year, is roughly about 1,500 kilowatts of electricity. So if your energy bill is more than 1,500 kilowatts, your company is probably in this, and you're probably now, and this is the key thing, the companies were registered for 3 or 4 years and weren't actually having to do anything. Last year was the first year where the finance director of your business had to get the checkbook out and write a check to Her Majesty's government and pay back. Now, it started off on a tapered basis and probably only 50,000 a year for fairly large businesses, but that will rise. There's also all sorts of complexities that if you don't meet your year-on targets, which are roughly about 20 or 25%, and there's probably people in the room that know more about it than me. I'm purely mentioning it as a driver for what we're about to look at. But if you're not hitting those targets, you can then start losing some of the exemptions on some of the other tax rebates that are happening. So it's a big deal for companies that are in there. But it also includes your gas footprint. Really bizarre situation. You're in it because of your electricity bill, but by saving on your gas bill, you can ease the pressure on it, because ultimately what they're trying to do is drive carbon consumption down. Now, whether you believe the global warming thing or not, it doesn't matter a bit. Brussels and the British government have signed up to reducing the target, and their biggest lever is price, either price on tax or price on the cost of energy in itself. So it's here, we won't get away from it, whether we agree with it or not. If we start finding icebergs growing back at a greater rate, that the legal system isn't going to change fast enough. We've got this imperative to reduce our carbon footprint. So it's really great when you don't have to speak about part of it. The man at the room will say more about this in the next presentation, but really low-hanging fruit actually could be quite significant. So we produced this graphic, it's on the website, but basically different places you could be saving large chunks of energy, perhaps totaling 50% of your running cost. Now, I visited a chocolate factory recently that's got a £6 million electricity bill, and frankly some of the stuff I saw was absolutely mind-blowing. They had pumps running, feeding through chillers, and the chillers weren't even in operation anymore. 70 kilowatts of drive motor just running, as one of the questions mentioned earlier. I think it was Steve from Bureau Happold, David. this building getting out of touch with what's actually happening. And there's some great businesses in the room here that are visiting. Colin Kerr from Kerco Automation. Their systems will override the entire building and really try and keep tabs on all these different parts and bring it all back together. But fundamentally, if you delegate the performance of your building, you can't abdicate from it. You can't just hand it over to an expert and not be interested. So the more insight we have, and that will come back into the low-hanging fruit. But really, it's a bit of a warning as well. I'm a big fan of Dilbert, but here's this low-hanging fruit. Wow, and he gets a poke in the eye. It's not all it's cut out to be. So please don't think that low-hanging fruit is going to get you out of jail. So I should have said, if you want to see that video, it's on tinyurl.com, low-hanging star. Have a look later, but it's really quite insightful as to the different areas where the energy comes. So what are our customers doing? Well, we saw some examples about people storing stuff. We've got some examples of people making stuff. There's maybe some new areas perhaps where we could do distilling, and drying is an area where heating and cooling is a large part of the demand. So what are the typical opportunities that we might see in these different areas? Well, people storing stuff, they've probably got existing kit, and there's probably all the aspects about usage, and that comes more into Andy's presentation than mine. People that are making stuff, as I was saying, they're probably heating something up and then cooling it back down again. Most factories have goods delivered at one temperature, be it butter or chicken or whatever the product is for food manufacturing, and then it cools down. Even factories where you're bringing in ambient goods and they're leaving frozen, a fish factory, for example, the chances are there's quite large heating demands on that site for washing and so on. So really that joining up the cooling and heating bit is part of what we'll be talking about. For distilling, there's 79 billion litres of ethanol produced around the world, and it boils at 74 degrees, and yet we use steam at 150 degrees. So maybe there's some thoughts in there of distilling could be done better with recovered heat. And then drying, I thought the biomass industry had absolutely nothing to do with us, and yet all these wood chips that people are doing, they have to dry them first. So we might see some areas where we could do drying processes by combining up heating and cooling. So Plan A, and people have jumped on this with Marks and Spencer's, and Plan B, Richard Branson's new thing of Plan B. Well, really what they're coming down to is they're saying plan it and monitor it and then act. And that's not a bad philosophy. It's certainly better than burying your head in the sand. But basically they'll be saying, let's have some low-hanging fruit. Let's use some existing data. And low-hanging fruit might get you to 10% of your total energy bill. Now that seems quite good. But plan will take about 3 months. Monitor will take another 3 months before you've got any data that's of any significant benefit, because probably there's some sort of ambient function going on that winter is colder than summer. And then another 3 months of implementing these things. And really, 10%, and it's taken nearly a year. Does that feel like a winning plan? It doesn't to me, because as we saw from the graphs earlier, the chances are your energy bill, never mind the carbon footprint, but the pounds per month will have risen by more than you've saved by tinkering around the edges. So again, there's another graphic. I'm a big fan of finding graphics on the internet that amuse me, and this one amused me even more so when I realised there's some sort of nuclear holocaust going on down there. I think that's a little bit extreme. I'm not suggesting low-hanging fruit leads to nuclear holocaust, but certainly there's a slightly better view down that path. So tweaking, that's essentially what we're talking about with low-hanging fruit. And there's some great images on the internet. Spanner, that's the one that came up first for low-hanging fruit. I've absolutely no idea what this guy's doing, but he's under tweaking when you Google for tweaking. There's a DJ. And this one, maybe this is what it's about, tweaking your sitar, tutor number 4. But that's not really what I'm talking about, and it's really down to the difference between what this man would think about tweaking, which isn't a sort of expression you would come up with him, or his more familiar approach to life, the hairdryer, which is a really, really naff graphic for Alec Ferguson with a hairdryer. I'm sure he didn't actually pose for that. That must be Photoshop. That's really what we're talking about. You can have tweaking, or you can have the hairdryer approach. You have to take the hairdryer approach with your energy consumption. Get right in its face, and let's see what difference we can make. So thinking differently, some great guys over the years have been talking about thinking differently and obviously are held up in high regard. The last one, Einstein, also is famously, along with these guys, also quoted as being the first author or statement for the definition of insanity. So the great and the good there, including Mark Twain and Confucius. But actually, what is the definition of insanity? There's some really interesting stuff on the websites under tinyurl.com. Definition of insanity. I didn't write this stuff down, but really it's the definition of insanity is repeating the same mistakes and expecting different results. And that sounds a really highbrow philosophy. Now, just when you're going to go and tell all your chums it was Confucius or Einstein, actually be very careful, because it was first attributed to the World Service Conference of Narcotics Anonymous, which maybe isn't the image you want to portray to your friends and colleagues, and it was as recently as 1981. However, I think it is true that the definition of insanity is making the same mistakes and expecting different results. We have to go about it differently. So what does that mean back to our plan A or plan B? Well, the first step you have to do is go in and recommission the plant. Again, as the question earlier was saying, does the plant drift from what it was originally intended to do? Absolutely. There is not a facility in the country that is operating as good as it was the day it went in. Things go adrift, particularly if there's a light touch to maintenance and so on. You have to get in amongst it and get the numbers down. It would be quite easy to save the 10 or 20% doing that. But the most important thing is that's not the end of it. That's the first step. The second step is establishing monitoring. I doubt there's many facilities in the country that have enough data gathering to deliver the future of total energy. They monitor a little bit round the edges, so they might monitor the gas bill. Do they monitor how much heat is being used in hot water systems at each and every individual location around the building? No, they don't. So how can you possibly know that you use that quantity of heat in that area and so on? If you don't measure it, you can't manage it. And the last bit is, what is this plan going to be? Well, I think what we have to do is aim for some immediate gains. We have to gain some good grace with our chiefs. They're the ones that are ultimately going to be spending the money for the bigger plan. So getting quick wins is really important. It's also an iterative process in establishing the monitoring. And let's be honest, it's a bit of a moving target. If you think that you're going to gather all the data and then jump in and start acting, life isn't like that. Things change around all the time. You could take 4 years of data before you had the perfect understanding of your process, and your process is probably changing over that time, and so on and so on. So really it's about thinking big. It's the hairdryer treatment on your energy consumption. It's about data and more data. I was really tempted to say data, but that sounded a little bit naff. So data is absolutely everything in this. And then this concept of total energy. Go in knowing that you want to be finding out the total energy consumption of the building, and then maybe you can do something. And set ambitious targets. You know, why couldn't we reduce the energy consumption of a facility by 40%? I've seen factories where that would be really quite easy to do. If you don't aim for it, you'll miss it. So a little bit ahead there. There's a great quote from an ice hockey player, a guy called Wayne Gretzky. And the one that really strikes me is, you'll miss 100% of the shots that you don't take. That sounds like my son's football team, in fairness. They sound like 100% of the shots they do take. But if you don't try it, you'll certainly fail. That's a truism. So a short video of what total energy meant to this chocolate factory that we were working with. So really what we have is some sort of production going on. And apologies, a student that was working for him at the time, a curious sense of humour. It's not meant to look like rows of turds going into the machine. But there's a heating process, heating it up, and then there's a cooling process. That is chocolate making. It's really, in that sense, quite simple. And for the 43 years that Star have been in business, we've only ever been asked about this bit. And in fact, in reality, we've probably only been asked about this bit, and they don't really tell us what's going on downstairs. We've started saying, why do you do that? Why do you need so many kilowatts? But basically what we're doing is we're heating up in this factory by burning gas. In their case, in fact, it was coal, so it was even worse than gas. And then we're cooling down. And what we said was, if we capture the waste heat and deliver it back into the heating process, And of course, there's no perfect situation. A lot of processes must be steam at 130. But when you start getting into it and measuring what quantity of heat, what time of day, you start realizing actually steam has been overused over the years in the sense that it's quite convenient. If you have to transport kilowatts of heat across a reasonable distance, then steam is quite good. But the reality is we quite often use steam at fairly low temperatures. So the brewing industry, for example, does a lot of pasteurization at only 60 degrees, and yet they'll be burning gas. And we come on to some of the graphics. I won't dwell on these too much because some of the numbers are very subjective. This was done a couple of years ago with energy costs being lower. But the concept is basically, if you throw energy away, it's gone. If you capture it and reuse it, you can offset that against your original energy bill. And the savings are quite startling. So I've also got some slides here, and the difference between being in working life and being at school is that you are allowed to copy so long as you say who it was and it's not plagiarism. So some colleagues of mine presented this as long ago as 2011 in Florida. I've never been to Florida. I didn't get to go on that trip. But there's some great slides, but I'll whiz through these because they're a little bit heavy for just now. But anybody that sees something that they're particularly interested in, go back and have a look. I'll maybe pick out a couple of slides and then use a summary. So David Blackhurst, who spoke earlier, and Danny McDougall, a colleague of mine, gave this presentation about what we achieved for Nestle. But basically, in short, it's a large site and it does all sorts of chocolate in Halifax, and it was burning coal. That's the basis of it. They had quite a lot of data on site. I wouldn't say it was perfect, but it was certainly better than typically what's seen. And they had a very strong background to the work that we do with them, which is natural refrigeration using ammonia. Basically, they see that company after company, time after time, have put in a gas and then it's been phased out. They put in a different gas and it's being phased out. Nestle, whether it's for environmental credentials or they just realise that the plant lasts 25 years if you're still allowed to use it. If you stop being allowed to use it after 15, then you've got a 10-year-old plant or 15-year-old plant with 10 years life in it. Surely that's a bit of a short-sighted approach. So Nestle totally demand to still be in business in 25 years, so they're laying it out. Lots of analysis was done in advance. They did gas-fired boilers, they did combined heat and power, they did boreholes for heat and storing energy and retaking it back at certain times a year. But really the option that came out, and it was a lot of analysis, it's on the next slide, they came out with a qualitative score that migration to a thermal coupling, as they called it, was certainly a pretty good option and gave them the best benefit. So as I say, it's pretty detailed. The short of it was also, we had a strong hard look at that 5.4 megawatt heat demand. And in fact, we only need 3 megawatts of cooling on the site. We're recovering 1.25 megawatts of heat if they want that, and it saves them a considerable amount. Now, it's quite embarrassing when you tell somebody something, you make a promise and then you get it wrong. And in this case, we made them a promise that they wouldn't use too much extra electricity by recovering the heat. And it's good science. If you throw heat at 40 degrees versus recovering it at 60, you should expect energy consumption to go up. Just the reverse of what Rob was saying about get the head pressure down. It should go up. We promised them it wouldn't go up too much. In actual fact, we'd underestimated how bad the kit they had originally. And their energy consumption has gone down by, I think it's on the next slide, by about 15% over the same period. So there's a bit of a detailed diagram. It's on the next slide, I think. So this was the plant which was installed originally. Sorry, get a bit trigger happy in the buttons. This was the plant here, and it's classic chiller plant. It's R22, which was one of the imperatives for swapping it out, but at the same time, it really wasn't terribly good when it was new. It's been looked after not very well, and it's just drifted. So it was all dirty, it was fixed speed fans, and what we installed was some heat rejection here. The key thing is though, we only reject heat if we can't reuse it. So it's far better to not run even the fans and keep the heat inside the process. It's really what's saving them. And in a very simple diagram, we re-looked at the Glycol facility and tuned that around a little bit as well. They've got 2 circuits of hot water The first is an open circuit where they're heating from 12 degrees to 60, and the second is a closed loop where it's going from about 40 to 60. Now, you'll notice here, if you're sharp-eyed, they're actually heating some of the water to 90, and we could have done that with a heat pump. We can now get up to about 90 degrees, but in actual fact, in this case, it made more sense just to do 12 to 60 and do 60 to 90 using high-efficiency gas boilers. So really having that total energy approach. And you'll see the difference here between the integrated plant, where we're focusing on the energy for cooling with sort of incremental heating cost, versus 3 different ways of energy for cooling, energy for the closed loop heating, and energy for the CIP heating. We kind of combined it as much as we possibly could. And I'll skip these numbers because they're a bit detailed, other than to say, just by doing that was about £750 a day energy saving. So, yeah, it was a 39% reduction in power over the same 15-week period by switching out from the old plant and capturing the waste heat. It's quite significant. Now, thinking back to the philosophy, if you like, of how to go about doing this, a subsequent chocolate factory we looked at, we were talking about small wins, medium wins, and large wins, and you can see just by the number of bubbles here that it's taking longer and longer to do the bigger wins. What they asked us to do, disappointingly, we gave them the quote which suggested they could save £1 million a year for spending 500,000, and didn't hear from the guy for 6 months. We contacted them, we tried to get in touch, and other stuff was going on that was more important than saving £1 million off his energy bill. But what we laid out were 2 different ways of doing it. The typical way of doing the project with a tender, an audit, feasibility study, design agreement, purchase spec. I mean, the clock is ticking all the way down here, and ultimately getting from July all the way through to a year plus in January for the commissioning. So no energy savings until this point here, really, other than the odd quick win. If we compress all this and really take that hairdryer approach to our energy, we can shorten the total project by about 6 months, which probably pays for the project. So all this concern about capital cost and investment, the harder and faster that you get into it, then the smaller the investment. And there's that same graph that Rob had of capital, aftercare, and operating. It really is about focusing on this bit here, but almost in another dimension of thinking about the heat as well as the cooling. So these are probably 2 simpler case studies that make it a little bit easier, just to set the boundary of what Star as a business have been looking at. The first is a district heating plant in Norway. So having thought about heat recovery and realizing that for 150 years our industry's been throwing away waste heat, all of a sudden we get an opportunity to start gathering waste heat. The next project that came along, these guys are sucking water out the fjord at 8 degrees and cooling it to 4 degrees in a town in Norway. And we take that roughly, in round numbers, 10 megawatts of heat from there. And then we add in the electricity to drive the system, and we deliver 15 megawatts of heat, heating the district heating from 60 to 90. So in a UK context, for example, the Clyde has a capacity of heat that far exceeds what the heating requirements of the city are likely to be in the future if we gather waste heat and use it. So why was that a little bit bizarre for us to be doing this project? Well, these guys are throwing away the cold. I tried several times to get them to install a data center here and capture the heat from the data center rather than cooling down a fjord and throwing the cool away, but they weren't having it. Very focused on energy, but only their own needs. And that's the town in Norway. So a new district heating plant is in here, taking water out the fjord, and then a reasonably complicated circuit on the water side. But the purpose of mentioning it in the 3 different phases is that when we look at it all together, we've got 3 heat pumps operating in series, but lots of areas where we're gathering heat, even to the extent of taking the heat from the water-cooled motors and putting that back into the system. And that's worth about 1% in the energy performance for them. So really trying to be gathering heat in every single area of the plant. We get 3 times as much heat out of the system as electricity that we put in. And that's the system in our factory as it was being built in Thornley Bank. and that's it installed in Norway. So this is the key number and all the data assessment and gathering. And on that particular day, we were getting about a 3.18 COP, slightly off the 90 degrees, so that's why that's just above, but certainly 3 times as much heat out as electricity in on a normal operating day. Here's the summary for the chocolate factory, and really what we're doing there is doing useful cooling at -5, whilst doing water heating at around about 60, and we get a COP of heating of about 3.39. Now, you have to point out at this point that much of the electricity is already being spent by the cooling guy. So although I'm talking about total heating and total energy, don't think that all the energy cost falls on the heating. The guy here who's doing the cooling, first of all, he's paid 75% of that electricity bill anyway. And in fact, in that case, because the plant wasn't terribly good in the first place, the energy bill was paid by the cooling requirements. So they're effectively getting free heating on that site now for their services at 60 degrees. And there again, you see the 2 systems, and we have 4 compressors, 2 of them throwing away heat and 2 of them capturing heat whenever possible. That really was the strong driver for Nestle, and as David was saying in a lot more detail, global warming potential is very high. Whether you think that matters to your business or not is up to you, but the really nice thing is, of all those refrigerants there, ammonia is actually the most efficient as well in terms of the operation. So it really is a win-win situation. So whether you're financially orientated or environmentally, you're not having to pay a penalty for being slightly better in the environmental perspective. Now, why does that leakage matter if that is a concern? Well, thinking back to the district heating plant that we had, they were planning to use R134A. They would tend to leak about 1% per year from a large system. That's actually quite good compared to some facilities, so we won't have to argue whether 1% is too high or too low. A large plant we looked at, and this is a concern of mine as we see more people interested in district heating and heat pumps for district heating, is that we forget about the global warming potential if these plants are using HFCs. So a 73 megawatt system that we were looking at in South Korea would have about 50,000 kilos of R134A in it. That would leak about 500 kilos per year. So apart from the financial cost of about £15 a kilo, which I think has doubled in the last 4 or 5 years, that is about 30,000 per year, doubling every 2 to 3 years. But here's the real shocker for me when I worked out the numbers. That plant, just a large facility admittedly, would be the equivalent global warming of 2.32 million miles in a Volkswagen Golf every year. That's why I don't think we're going to find the legislators backing away from this. They've decided HFCs are under pressure. I'll be really surprised if they don't get a severe impact on their operation. The UK is a little bit interesting as well. District heating isn't everybody's interest, but the government are incentivising the use of river water. So here's the Clyde here with the Armadillo and so on. Each of these buildings, instead of burning gas, could be taking heat out of this river. And as the technology gets better and better, the COP, the efficiency gets better and better, then some significant savings. The government are also incentivising this. From all the incentive schemes I've seen and people talk about, solar panels and biomass, this seems to be as good as any of them. And really what we're saying is that, sorry, one slide too far, that you can almost get to the point where you can heat the building for free because the incentives are good enough if you're taking heat out the river. So there's just a couple of snippets about how life is different round about the way Star are looking forward in the future. But really I think what we're going to see over the coming decades is this approach to total energy. A recent study done in London by Bureau Happold showed that there's enough heat, waste heat in London, if harnessed by heat pumps, to heat all of London. So if we're going to come down to any significant difference, it's probably we're going to see that people realise that burning fossil fuels or any type of fuel just to heat our buildings to 21 degrees is a slightly outdated way of doing things. We've been fascinated by it since we were cavemen, but we don't live in caves anymore. So that really is the main point. Thank you.